So, where are we? So, we were in chapter 7, I guess. Summation of infinite series. Summation from infinite. This is chapter 8. Chapter 7. So we are kind of on the way to discuss about the infinite series. Most important thing to realize that nobody can, or the whole world cannot add an infinite series. Regardless of how much you add, infinitely many terms will remain to be added. So it cannot be done. So as a result, we have a definition of an infinite series, sum of an infinite series, we have a definition. So it is almost like the sum, but it's not the sum. What happens is, say suppose you have, say positive terms, you have a container, first you put A1, then you put A2, if the sigma A series is sigma AM, you put A1, then put A2, then put A3, then put A4. It is convergent means if you put your I, suppose you are, that idea is very important. Say suppose you are putting water, so you say you put A1 water first, then A2 water, like that, A3 then, A4 then, so only positive terms here, it doesn't matter. Then series convergence means sum of the series is, say, S means if you put your I here, when you look at the water level, it does not change. That is the meaning, physical meaning of a convergent infinite series. You are adding terms continuously, but you look at this way, close the eye, water level, it doesn't change. Then if you think your eye is not sensitive enough and you improve something like cameras you use in Olympics, we have very powerful cameras. Even if you look at by a more sensitive camera, in the well, again, water level doesn't change. But to the contrary, we are adding water continuously. However, in this given order, first A1, then A2, then A3, then A4, that way. So that is the meaning of sum of an infinite series. To a layman, to a man in the street. But in our case, we say, we take sum of the first n terms, we denote it by Sn, sum of the first n terms. Then, if there is a limit, n goes to infinity. If there is a limit s, then we say that the sum of the infinite series is s. So I am telling it again and again, it's not really a sum. So as a result, some amazing things are expected from an infinite sum of a series or sum of an infinite series. So we need to be very careful. In A level, you have only, either collapsing sum or partial fractions. Then you can A level problems, you can always find Sn. Then you can always find the limit of Sn. But when you go to the university, not to engineering faculty but to science faculty, engineering faculty also uses tests. These collapsing sums you can find Sn, always you can find the limit of Sn. Then actually in A-level problems you always get the number S is finite. It has a limit and it is convergent. It has a limit and it is a real number. So as a result, somebody who really does not go through, some of an infinite series in a rigorous way, they have a very wrong impression of infinite sum. For instance, engineering faculty students, I don't know now. Now there are some people, I suppose, who know some pure maths, but long ago, to them it is just like A level, infinite sum. But it is very important, after you pass the A level, then the sums you run into, you cannot compute Sn. No way, you cannot compute. As a result, there are different tests to determine whether the series is convergent. If somebody gets really sick, when you go to the doctor doesn't kill the patient, no, but there are different tests, your urine test, blood test, I don't know, vein, this and that. By doing that, they decide, I guess, what's wrong with the patient. That's not, I guess, correct always. Medical science is not an exact science. So it is kind of little funny, but and it works for many people, many patients. That's why it lasts and they are very well. But still they say not enough money, no? Salary, regardless of how much they are paid. So very first test was that if you are considering the sigma A, because now what are we are going to find what are the tests that we use to decide whether a series is convergent or divergent. Because we cannot find, we can give you the square root of 1 over log n, n going 2 to infinity. There is no formula for log 2 plus log 3 plus and so on plus log n. This cannot be simplified. Regardless of the fact that it cannot be simplified, we want to know whether it gets close to like my picture. When you add more terms continuously in this order, however, first term, then second term, then third term, and so on, whether there is some limit. Now, I guess we should do it, or I should ask you to do it after this test. So tests are very important. So very first test was that we learned if limit n tends to infinity n not equal to 0, who an doesn't converge. This is if, then sigma A diverges, DGS. This is the very first test that we are, I guess we learn in finite series here. Then we have the Cauchy criterion, no? And using Cauchy criterion, we proved that sigma 1 over n diverges. There is another theorem, I guess we will be learning it today. I hope so. Then there's this alternating series test. It is all, it is the only time you get this thing, but it is very important. So one other term, by the way, that sigma 1 over n, this series diverges. We have shown it, and this is called harmonic series. I suppose you know You do music, no? You may know sometimes harmonic series. It's related to music. Harmonics. This is whole harmonic series. Harmonic series diverges. So that is an amazing thing because when you are adding so many terms, after sometimes the terms you are adding is absolutely negligible. Absolutely negligible. Very small. So that teaches us a lesson that just because of something is very small according to the human eye or according to the way we think, doesn't imply that it is very small. You add one over n, you get infinity. I mean, there is no bound. It goes all the way to infinity. And then alternating series test is you have some sequence decreases to 0. Then test is minus 1 to the n going on to infinity converges. Did we go through this? Did we prove it? I suppose this is on the alternating series test, this is called. I think we passed this, no? Yeah. So you can prove that this is convergent. I suppose I did not.
Yeah, we have proved.
We have proved, no? So as a result, if you put minus 1 to the n divided by n, even though sigma 1 over n diverges, sigma minus 1 to the n divided by n converges by alternating series test. It is very important that it should be decreasing and limit must be 0. Otherwise, I mean, if the limit is not 0, you know from our very first test that it diverges. So I suppose these are not important. Sum of non-negative numbers. Sum of non-negative numbers, I mean, it's something like you are adding a finite number of terms. There are some similarities. When you are, if you have plus minus terms with both plus sign and minus sign, then things get very complicated. Sum of non-negative numbers, when you have only non-negative terms, then life is easy, very easy. So here, I guess I went through this. I am on, according to the book, page 170. I think we discussed it a little bit, no, did we?
Yes.
So it says if you have A and B, a formal series of non-negative real numbers, then the series is convergent if and only if partial sums are bounded above. No? I mean, that is very clear. If an increasing sequence is bounded above, then it converges to the sup of the sequence. So theorem 7.3.1 is about that. Then this comparison test is again a very small important one. Comparison test is one test. Comparison test. You know comparison test. In real life also we compare. No? In USA they say you date the mother, marry the daughter. What it means is when you associate with the mother, you will learn a lot about her. Quite often, I guess 99.99 times, daughters behave like their mothers. So that is a good way to, I mean, if you go there, sometimes some of us like to marry, say, when you are US American girls. But after this current president, it may change. You know this guy? What is his name? Trump? He is highly anti-American. He doesn't think that way, but he is highly anti-American. So, comparison test, you have to compare. For instance, if a man is very, burglar or murderer or something, then if he has sons, people say, oh, he's son of this guy, expected to be very nasty guy, or him to be a murderer, etc. So comparing is a big thing in real life also, very big thing in real life. Comparison test in series also, not only for series, the integrals also comparison test comes, but it's sometime later. But if you look at the tech comparison test, this is very important one. I am emphasizing the tests because once you learn the test, all the tests, if you get a problem, you apply every test and see whether you can come to a conclusion. Because you don't know which test to be applied. You don't know, you try one and one. Somehow come to a conclusion. So this one is intuitively, no need to be proved, no? He is stating not be less than or comparison test according to him, you have AM less than or equal to BN. So I guess according to the book, n greater than or equal to m. If this one bigger one converges, the smaller one naturally converges. Now when you add big numbers, if it gets closer to some number s, then smaller numbers must also get closer. So comparison test is intuitive. It says if the bigger series converges, then the smaller series converges, and conversely, if the smaller series diverges, then the bigger one diverges. So proof, I guess, I don't have to really, and this proof 7.3.1, he says, you can prove it, no problem, but you need to remember the fact, and you have to feel it in with this one. If you are adding some bigger numbers, as a result of adding bigger numbers, gradually, if the sum is getting close to some number, then when you are adding something smaller, it is close to some other number. So, proof is very simple. You don't want me to prove it, no? You can prove it easy. Then geometric series on page, I guess, 171. That is very clear when you have the geometric series. However, though this is innocent, geometric series, O-level people, they also do they learn geometric series in O-level? I can tell. So, but
only up to finite.
Finite number of times, yeah. Geometric series test is very innocent, but it is the most important one. Other tests, like ratio test, root test, we have to learn later, they use geometric series. Very important. What it says is, if you have sigma x raised to the power n, converges if and only if mod x less than 1. Then that looks simple, he says something. Sometimes I cannot, some others say that it is so innocent, but even Adolf Hitler was a vegetarian. Although some people think, some people, not some. Intelligent those who are, some people those who are not intelligent thinks that if a person is a vegetarian, he is good. I don't think at all. Right? You cannot decide the person's character by what they eat. Though they are very nasty. So anyway, so 7.3.3 says let x be a real number if mont x greater than 1, then the series is divergent. If however mont x less than 1, then the series is convergent, and n going 0 to infinity x to the n is 1 over 1 minus x. Here he is given from 0 to infinity. So actually what we get is, if you have the geometric series AR to the n going 1 to 0 to infinity, then the sum of the infinite geometric series is A over 1 minus R. A is the first term and R is the common ratio. You can prove it very, very easily, but you need to know it. Then he says this is Cauchy criterion, next one. Again the name is different. This one is called, other people call it Cauchy condensation test. Because you have A1, A2, A3, A4, A5, A6 and so on. Convergence or divergence of that series can be decided by adding 2k, 1A1, 2A2, 4A4, 8A8. So only a very small amount of series, terms in the series will decide the convergence or divergence of the series. So that is, in that sense, it is very important. I guess he has a proof, because proof is there. This morning I wrote something. Anyway, the same proof, I guess, but sometimes when I was an assistant lecturer before I went to USA, so this was the most important section for me. Because students, I give so many problems, discuss the convergence, and they were very excited. So you also must be good at this. And then this. So, what it says is, you have two series. One is n going 0 to infinity. So, that is A0 plus A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 plus A8. So, A9 we going, oh. This series. And the other series is 2n A2 to 3. You are adding, if you put AC n equals 0, you get A1, then 2A2, 4A4, 8A8, 16A16, like this. What the theorem says, both of them are either convergent or both of them are divergent. One series converges if and only if the other series converges. Proof, of course, in the book, but I mean, without writing the proof, I just write the idea only. You say Sn is, of course, k going 0 to n, or k going part. Say 1 to n, and Tn, that is the partial sum of this series. A0 is not, it doesn't matter whether it is there or not. Let's put A1. Let's put like this, like book. It doesn't make any difference. Tn is, however, 2k, A2 to the k equals 0 to infinity. When you put k equals 0, you get A1, not A0. No? So Sn is, however, Sn is what? A1 plus A2 plus A3 plus and so on plus An. Tn is A1, and you put k equals 0, you get A1, then 2A2 plus 4A4. Bingo, 2 to the n. A 2 to the n. So I guess we are proving since both of them have positive terms, partial sums are increasing. For we know that increasing bounded above sequences converges. Sn is increasing, Tn is increasing. So if we can prove that Sn is bounded above, if and only if Tn is bounded above, and Tn is bounded, no, that's the here. Proof is in the book, but I am saying if you take an n, let me write here. N of less than or equal to 2 to the n plus 1 minus 1. That is 2 to the n plus 1 greater than or equal to n plus 1. So then Sn is 2 to the n plus 1 minus 1 is what? This is A1. I am still talking about Sn, not T. A1 plus, when you put n is equal to 1, I don't know Sn is to A1 and plus A2 plus A3. I have a bad throat, I don't know why. A4, A5, A6, A7, A8, then what I do is here, I group them like this. Then the last one will be what? I am going to go to the n plus 1 minus 1. So that is the last term will be a 2 to the n. Then a 2 to the n plus 1. Bingo plus a 2 to the n plus 1 minus 1. This is again one block. So you can see here very easily. This is the standard equal to A1. This is less than equal to 2A2 because this is increasing. This one is 4A4. Next one is 8A8. Window. Last one is 2 to the n. A2 to the n because from here to here there are 2 to the n terms. So S2 to the n plus 1 minus 1 less than or equal to this thing. This is not the proof, but the idea of the proof. So here then s to the 2n, 2 to the n. The way I am writing is correct. 2 to the n plus 1 minus 1. So here. Therefore, we have Sn less than or equal to Tn. Is it? Similarly, then 1/2 Tn, Tn is here is 1/2 Tn. Therefore, then we have shown already less than or equal to Tn. You can use induction to nice write it better, but this is the idea. 1/2 Tn is 1 A1 by 2 plus A2 plus 2A4 plus 4A8 plus and so on plus 2 to the n minus 1 A 2 to the I divided by 2. So you get this thing. So you can say, however, this is less than or equal to A1 by 2 less than or equal to A1, A2, then A2, 2A4 less than or equal to A3 plus A4. Here, because A3 is big, no? Instead of, if you had, there is A4 twice, since A3 is smaller, A3 plus since A3 is bigger, I'm sorry. Here you have 4A8, so I'm saying A5, A6, A7, A8. This is smaller because this guy is bigger than this because it is a decreasing sequence. Right? Then plus here you have A2 plus here you begin from A2 to the n minus 1 plus 1 A2 to the n minus 1 plus 2 bingo plus A2 to the n. This is true because n is decreasing. So however, what is this then? This is exactly S2 to the n. S2 to the n. Therefore, T, 1/2 Tn less than or equal to this, S2 to the n, therefore Tn less than or equal to twice S2 to the n greater than or equal to Sn. So that is the proof actually. You can write this rigorously using induction. But the idea is this. Now you can see if Sn is bounded above, so there is some capital M such that Sn less than or equal to capital M. Therefore, 2 S2 to the n less than or equal to 2n. Therefore, Tn less than or equal to 2n. So, if Sn is bounded above by capital M, Tn is bounded above by 2n. And here, if Tn is bounded above by capital N, then Sn is bounded above by capital N. So, Tn, since both are increasing, one series is convergent if and only if the other is convergent. One Then convergence or divergence of series very well. That's very important when you are going to do analysis. Shall I rest? Before I proceed, I want to say something about alternating series test. Something Buddhist. I wrote by this pen or some other. I used the black pen, no?
That's a black one.
This is black. This part is light blue, is it? Anyway, you know this alternating series A1 minus A2 plus A3 minus A4, A5 minus A6, bingo. So we prove that this is convergent using a Cauchy criterion, no? Cauchy criterion. That is sigma A converges if and only rho epsilon. I mean, the rush I like to write this much as a characteristic. For each epsilon greater than 0, there it is, say some n epsilon belongs to, is a plus such that for each n greater than, here I am writing, considering this one with not from m, for each n greater than m, greater than or equal to a over a, but it doesn't make any difference. N epsilon sigma n m a k a, this sum is less than epsilon. So this is the Cauchy criterion. To show that the series convergent, we use the Cauchy criterion. So then we get the sum, say sum, okay, like a m plus 1 if you use the Cauchy criterion, you get sigma minus 1 to the, say k, some k going from, I guess, say m plus 1 to say n. This one less than, we need to prove something like this, no? So what I am trying to show you is that this is like minus 1 to the m plus 1, am plus 1, plus minus 1 to the m plus 2, am plus 2, plus plus minus 1 to the m plus 3, am plus 3, minus 1 to the m plus 4, am plus 4. Bingo, like minus 1 to the n. Say we want the absolute that this thing should be less than epsilon, not graph. To want to prove this series converges, then what happens is you pull out minus 1 to the m plus 1 factor. Then inside you have am plus 1 minus am plus 2 plus am plus 3 minus am plus 4. Something like this. I don't even write. Doesn't matter. Let's write some. Minus 1 to the some power, whatever it is, a. This is what you are going to get. So, what I am trying to say is, now this one is 1, this is equal to am plus 1 minus am plus 2 plus am plus 3 minus am plus 4. Diggo, sum, whatever, minus 1 to the some power, whatever it is, depending on if it n doesn't matter, minus 1 to the c. I'm not interested in. This is the absolute value of this thing. I mean, you can see this very easily. Can you see here? This first term am plus 1, in absolute value that is the biggest. No? So, no matter how many terms you add, am plus 1 is bigger than plus or minus of the other terms. Always. And we know that am plus 1 greater than or equal to am plus 2, greater than or equal to am plus 3, greater than or equal to am plus 4. Like this, we know that. But now, this is dominance come from am plus 1 actually. This one is less than or equal to am plus 1. Always. So let us assume that you had 3. In fact, this is not the proof, but to convince you, I don't know whether you noticed it. Suppose you are adding 3 terms you had. This is like this, not this is like, this is exactly am plus 1 minus am plus 2 minus am plus 3. Since it is decreasing, this term is positive. As a result, this is less than or equal to am plus 1. But if you had 4 terms, am plus 1 minus am plus 2 plus am plus 3 minus am plus 4. Here you can say again, this is equal to am plus 1 minus am plus 2 minus am plus 3. Again minus am plus 1. So, less than or equal to am plus 1 because this is positive, that's also positive. So, regardless of how many terms you have written after the first term, always this sum less than or equal to am plus 1. So, that is something to be remembered also, not only for the ordinary series test. You know this one also, I guess. I think I write factorial in plus 1, certain, and plus 2, bingo. This is less than or equal to 1 over factorial n. Less than or equal to 1 over factorial n. So the first term dominates other terms. it doesn't matter how many terms you write, it is less than or equal to the first step. I mean, that is essential, the proof of ordinary series test. Something to remember, because when you are an analyst, though, I mean, we are not going to cram certain things, we have to know why, as if you have crammed. Okay, then we discuss about the then Cauchy. We call it condensation test, by the way. He said, what did he say? He said Cauchy criterion, so it has a different name. So I guess his lemma 7.3.6 proof may be what I wrote on the board. I didn't really go through it. You can, it is just nothing but just writing. But I wrote actually. Only thing he is writing a rigorous proof using induction. I mean, that's the same thing. But I wrote is the essential part of it. So this is a very important test, Cauchy condensation test, to prove some, say, convergence or divergence of some series. That's the only way I know for some series. You need to remember here, in alternation series test, Am is decreasing and limit is equal to 0. For Cauchy condensation test, limit part is not there, only decreasing. What it says is, if sigma n converges, if and only if sigma an to a2 to the n converges, very important one. Actually, there is a application here right away, lemma corollary 7.3.7. Let's go to that. It says corollary to Cauchy condensation test. What it says is, let Q greater than 0 be a natural rational number. I don't know why. Because we haven't defined. Did we define irrational powers? We did.
Yeah.
We did say, I wonder why you're not right. Say, I would say, let Q greater than 0 be a real number. We know powers. No? Then the series sigma 1 over n to the q is convergent when q greater than 1 and divergent when q less than or equal to 1. Actually what he is saying is sigma 1 over n to the q converges if and only if q greater than 1. That's so from that also you can say sigma 1 over is equal to sigma 1 over n going 1 to infinity. Here power is 1. Since it is not strictly greater than 1, this one diverges. So this is very important one. Because we can prove sigma 1 over n diverges without this test. What we did before, I was writing 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. This block sum is greater than 1/2, then 1 over 5, 1 over 6, 1 over 7, 1 over 8. This block sum also greater than 1/2. Let me write only one more. I don't know, my throat is very bad. 1 over 13, 1 over 14, 1 over 15, 1 over 16. So this is greater than 1/2, this is greater than 1/2, this is greater than 1/2, this is equal to 1/2, this is definitely greater than 1/2. So, now if you are adding some infinitely many terms, each term is greater than 1/2, there is divergence. No? If you use that test and say this is divergent, you just say it. You don't know, somebody asks. You can say, of course, it follows from the theorem, but it's not clear. No? It is not clear, but of course it is true. Always, if you can, especially if you want to be an analyst, always it is very important to have the proofs which are clear. If you know it, you get guts. I mean, you can apply this test, sigma 1 over n to the q, and if and only if q greater than 1. And in this case, 1 over n is, power is 1, therefore is divergent. It is true. But that kind of proof is very important for you, I mean, when you are going to do studies. And you can, this one you can prove this way, this is the proof. And sigma 1 over n squared also you can prove without anything. This one also converges. You can say q is greater than 1, definitely. But there is another way of doing it. Sigma 1 over h squared is the sigma 1 over square. 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, and so on, say 1 over 8 squared. This is Sn, no? For sigma 1 over square. You can write this one is equal to 1 over 1. 1 over 2 squared less than or equal to 1 over 1 times 2. This one is bigger. Right? Then 1 over 3 squared is less than or equal to 2 times 3. This 1 over 9 is smaller than 6. Then 1 over 3 times 4. 1 over 5 times 6. So 4 times 5. Ringo, ringo, ringo. 1 over 10 times n minus 1 times. Then you can see that this is equal to actually. This is 1. You can find the partial fractions here. 1 over 1 minus 1 over 2. 1 over 2 minus 1 over 3. 1 over 3 minus 1 over 4. 1 over 4 minus 1 over 5. Ringo, ringo, ringo. 1 over n minus 1 minus 1 over 4. So this is just not equal. You get cancelled, no? So you get 2 minus 1 over n. So Sn is always less than or equal to 2 minus 1 over n. Therefore, here Sn is increasing. This is definitely less than 2. Sn is increasing and bounded above by 2. Therefore, sigma 1 over h square converges. So that is that. It's good for you to know. Because if you are going to depend on to prove something very elementary, if you are going to use the very heavy weaponry, I mean, if USA is going to war with Vietnam, they were there. If they had chosen use the nuclear weapons, they would have won. But then there is no Vietnam. So if you can do problems using basics, that is much better for your strength. Then one log n we didn't do. I may sometimes assign some bunch of problems not from the book for you to be concrete about using the facts. Here, let's read this remark 7.3.8.
Okay.
This is an important one. You are not going to do it, but some background knowledge. The quantity sigma 1 over n to the cube, when it converges, is called theta cube. The Riemann theta function of Q. That is called Riemann theta function, theta cube. Theta cube is equal to sigma 1 over n to the cube. However, q greater than 1. Because if q is equal to 1, there is no series, no, it is infinite. This function is very important in number theory. Very important. And in particular in the distribution of the prime numbers. Prime distribution of the prime numbers not known. Prime numbers are very difficult actually. Very difficult. Extremely difficult. There is a very famous unsolved problem regarding this function. Very famous one, called the Riemann hypothesis. Name is Riemann hypothesis. But to discuss it further is far beyond the scope of this text. I mean, we cannot even write that thing. I will mention, however, that there is a US $1 billion prize and instant fame among all mathematicians attached to the solution. So, if you can solve Riemann hypothesis, you get $1 million US, $1 million. Not only that, right away, I mean, you will be a big hero in the world of mathematics. I also actually have tried, because I am somewhat good at complex analysis. This is coming from, though this looks real, it is complex. Thought about quite a lot, but couldn't get anywhere. Other problems I got somewhere, with this problem couldn't get anywhere.
Sir, can you explain it?
The problem? This is like sigma 1 over n to the cube, n going 1 to infinity. I don't know how to write even theta. That now cannot remember. Not this way. Something like this. It's like dying singer. This is called theta cube. Riemann theta. Is it ETA zeta function? Riemann theta. So this now I cannot tell you the problem. Now this is defined on real numbers. So Riemann theta function. If this is the real plane, q must be greater than 1. So here is 1. So for these values, Riemann zeta function is defined. But if you learn complex analysis, this can extend. It's called analytic continuation. Analytic. There is a method in analysis to extend to the whole complex plane. However, not to one, you can q is equal to 1. No sense. So that is called, then you write that guy. This one is correct, not that one. Z I said. Z I said this. Sigma 1 over n to the Z. You don't know how to get complex powers. No? So this function, this is very famous function. So then gamma function comes. You don't know gamma function. Then I guess I should not say anything now. But I will try to see whether I can present an understandable approach to this thing. This Friday, today's Wednesday. This Friday or next day, just to see. I mean, you like to see it? You get the functional equation. I am within 3. I mean, you just did A level. I guess your knowledge is very good for the time being. And anyway, so the function is, this thing is something like this. Zeros of zeta function. Can you imagine this is going to be 0? Sigma 1 over to the q, you extend to the real. So here is 1/2. This thing is called critical strip. Critical strip. And whether zeros lie on this line, all the zeros so far, I guess to this day, I didn't check about it. They lie z equals 1/2 on this line. So, but it's all the zeros that we know lie here, but the problem is that all of them lie here. That's a big problem. I will, you don't know gamma function also. That's the problem. We have to do after, we have to study integration in this course. We are learning. After integration course, again, however, quite a lot of complex involved. You know only A level complex numbers. They cannot do. Anyway, once you extend this thing to the whole plane, that is called, this is Z, I think, my Z is like, look. Zeros of this function. These are very big numbers here, but good thing that you asked. I mean, I will try to say within 10-15 minutes, you have to know that how it was extended to the complex plane and a lot of things to be done. But it's good that you are curious. I was like you. I was not able to try for this problem. So I thought, but somehow I know a lot of complex analysis actually. Material wise, I have not done research. So, because the thing is, this one is connected with what gamma function, Riemann zeta function is a very big for you. very big analysis. If you solve one of them, if he is getting $1 million, we also can ask him no, $500. It's good that you are curious about it, but that, I guess, not, I shouldn't say it's not a good problem to try, but you have to have a complex analysis background. At least you must learn. I told you, algebra of complex numbers, I did not give the number,
Yeah, of course.
that you can read by some few days. It has no analysis at all, not at all, not at all. But about numbers, complex numbers. How do you compute sin 1 plus I? How to find something like this, 2 plus I root of 1 minus I. It must be, How do we do this kind of thing? It has no analysis. It's sort of like an engineering book. Good to know it. I was excited when though it has no analysis, I was very excited about it. Some people, those who have read, they are calling me to, this book is in the OUSL, write a separate book to put in the market. Now I don't have money. When I say I don't have money, when I was writing the book, to publish a book, it cost like 1,50,000. And it is a hassle that I have to keep the books at home. So that's why if somebody is like your tuition student, if he comes, if he agrees to publish, I could write it. I don't know. But I will try to tell you something somewhat close by. I have to prepare for it because you don't know complex and gamma function, etc. Maybe I have to prepare to present the problem. But it is very important one. What is amazing is when you look at 1 over into the sigma 1 over into the cube, even when it is real, one cannot guess how can they be related to prime numbers. That's the thing with mathematics. You always go to unexpected things. Unexpected things, quite a lot. Very exciting. I learned about this thing when I was in USA. I tried to come to a level where I can sort of handle the situation. I could not. So in a sense, I am not a good person to explain the problem, in a sense. But complex analysis is amazing, very beautiful. Oh, except more beautiful than I say when I was teaching at the Columbia University. I used to say, oh, complex analysis is more beautiful than any girl in Columbia University. Some people say, why? No, I'm saying, if a girl is beautiful, you see from your human eyes. The beauty of complex analysis or analysis, you have to see something above your eyes, called the brain. Beauty of analysis is seen by the brain, not by the eye. Beauty has, taste is, observed by tongue, like that. Music is ears, beauty is by eye, normal beauty. Here the problems in this section are I was thinking that the very first section about finite sums, no need to do the solutions. No, like 7.2, then 7.3, they are important. And actually 7.3.3, even now you can do it. Let sigma n be an absolutely convergent series. You know absolutely convergent means you put the absolute, take the absolute of a real number such that mod absolute an is equal to 0 in going 0 to infinity. Show that an is equal to 0 for every natural number n. Can you do it? Now, can you tell me the proof? Oh. Can you tell me the proof?
Proof by contradiction.
Okay, can you say?
So suppose there's a natural number n such that a n is not equal to 0. Thus mod a n is strictly greater than 0.
Okay.
Clearly choose a natural number capital N such that it's bigger than simple n.
Very simple.
The first n we choose that such that a n is not equal to 0.
Okay, okay.
Then clearly simple a n is strictly less than sigma 1 to 0 1 to capital N mod a n. Then when you take the limit, this side is a simple a n, it is not equal to 0. This side is going to be it's not going
Do you understand his proof? What he is saying is assume that there is one say k such that mod a k is not equal to 0. Then he is choosing some capital N or simple n such that n greater than k. Then Sn is greater than or equal to ak. Therefore, limit of Sn cannot be 0. That is ak. So it's a contradiction. Then, yeah, in previous problem also you can do, but we don't have to think about it now. Rearrangement of series, that is a very exciting section. Rearrangements. That's what I have been saying, that if all the terms are positive, no matter how you rearrange, infinite sum remains the same. It doesn't have to be positive if the series is absolutely convergent. Absolutely convergent means you get sigma mod a. Then also by rearranging, sum will not change. But if it is convergent but conditionally convergent but not absolutely, then the sum may change. So, this is true for integration also, and all kinds of things here. Rearrangement of series. What's the time now? Happy? Okay,